Hey everyone, and welcome. Today we're tackling a Leetcode problem called maximum area of longest diagonal rectangle. It sounds a bit wordy, but don't worry, the core idea is pretty straightforward. We'll break it down piece by piece. Alright, let's look at the official problem statement. We're given a list, and each item in that list represents a rectangle. It gives us the length and the width. Our job is to sift through all these rectangles and find a very specific one. So, what are we actually trying to do? The main goal is to find the rectangle that has the longest possible diagonal. You know, that line that cuts from one corner to the opposite corner. Once we find that specific rectangle, we don't return the diagonal's length, we return the rectangle's area. Now, here's the important twist. What happens if we find two, or even more, rectangles that all have the exact same diagonal length, and that length is the longest one we've seen? In that case, we have a tiebreaker. The rule is simple. Out of the tied rectangles, we pick the one that has the largest area. Let's walk through the first example to see this in action. We have two rectangles, a 9 by 3 and an 8 by 6. For the first one, we can find its diagonal squared, which is 9 squared plus 3 squared, giving us 90. Its area is 27. For the second rectangle, its diagonal squared is 8 squared plus 6 squared. That's 100, and its area is 48. Since 100 is bigger than 90, the second rectangle clearly has the longer diagonal, so we return its area, 48. Now, you might have noticed I was using the diagonal squared. This is a really common and useful trick. To find the actual diagonal, we'd need to use the Pythagorean theorem, which involves a square root. But square roots can be slow and sometimes lead to tiny errors with decimal numbers. The thing is, we don't actually need the real length. If the square of one diagonal is bigger than the square of another, then the first diagonal must be longer. Comparing the squares gives us the same result, but it's faster and safer. So our overall strategy is really simple. We'll just go through every single rectangle, one by one. We'll need a couple of variables to keep track of the longest diagonal squared we've found so far, and the area that goes with it. For each rectangle we look at, we'll calculate its properties and then decide if it's the new best one, or if it's a tie that we need to handle. After checking all of them, the area we saved will be our answer. Okay, here is the complete code for our solution. It's pretty compact, right? Let's break down exactly what each part is doing so it's crystal clear. First, we set up our trackers. The variable we can call max_dia squared will store the largest diagonal squared value we've encountered, and max area will hold the area of the best rectangle we've found. We initialize both to 0. This is a safe starting point, because any real rectangle will have a positive diagonal and area, so the first one we check will automatically become our initial best. Next, we start a loop that goes through each rectangle in our input list. For each one we pull out its length and width, which we can call L and W. Then, just like in our example, we calculate the diagonal squared by doing length times length plus width times width. We also calculate the simple area, which is just length times width. This is the heart of the solution. First, we check if the current rectangle's diagonal squared is bigger than the best we've seen so far. If it is, we have a new champion. We update both our max_dia squared variable to this new value, and we update the max area to the area of this new rectangle. But what if it's not greater? Then we check if it's exactly equal. This is our tiebreaker condition. If they are equal, we update the max area to be whichever is larger, the one we already had, or the area of this new rectangle. Finally, after the loop is done, we just return the value stored in max area. So what's the performance like? For time complexity, it's big O of n, where n is the number of rectangles in the input list. This is because we have a single loop that just goes through the list once. It's very efficient. And for space complexity, it's big O of 1, or constant space. This means we use the same small amount of memory, just a few variables, no matter if the input has 10 rectangles or 10,000. Let's quickly recap. The main takeaway here is that sometimes the simplest approach, just checking every item, is perfectly fine and efficient. The second big idea is the trick of comparing squared values instead of the actual values to avoid messy calculations. And finally, always read the problem carefully for those tiebreaker conditions. They often determine the entire logic of your comparisons. And that's it. Hopefully this explanation made the problem clear. If this was helpful, please hit the like button, subscribe for more breakdowns, and feel free to ask any questions in the comments. And hey, if you're feeling generous, there's always the Boba Fund. Keep coding, and I'll see you in the next video.